This is the video notes for 9.1c, Interpreting Univariate Data. We start off with this notes by describing the distribution shape. There are 4 different shapes that you can have when you're talking about statistical data. The first one is symmetric, and it's going to look like this here on the right in this box. It's going to look like this one right here, symmetric. When you have a symmetric data distribution, the data has approximately the same distribution on each side. And honestly, the important word is approximately the same. Okay, so it doesn't have to be perfectly symmetric, but if it's pretty close to being symmetric, we call it symmetric. Uniform data is our next one, so that's over here. So uniform data is flat because every single data point is the same number. So the data has the same number for all values. Honestly, uniform data is quite boring because it doesn't show you what's happening with your data set. So for example, let's say I did a survey of the class and I asked everyone how many siblings they have, and they all told me that they had 2 siblings. That would be uniform data, and honestly not very interesting because it's just all the same number. Our next type is skewed left. So this is skewed left right here. And I know it's skewed left because this is where the tail is. It kind of is spread out here to the left. So data that trails off to the left is considered skewed left. Okay. Then our next one is skewed right. For skewed right data, this one right here, you see the trail, it trails off here to the right, kind of peters off. So this one would be skewed right, data that trails off to the right. Okay, now let's do some examples and see if we can name the shape of these distributions. The first example that we're going to do is right here. This one would be considered skewed right. Do you see the little tail right here to the right of data? So this one is skewed right. Okay, then let's go to our next example. Over here, this one is symmetric. I know it's symmetric because it looks very even. It has a nice peak where the center is, and then both sides generally go off evenly. Our next one is this box plot, and this one also is skewed, just like our first example, and this one is skewed right. So you see over here, it has a long whisker here on the right, so this is skewed right. Okay. Now we're going to talk about different measures of center. So there are 3 measures of center that we have been talking about the last few days. We've been talking about the mean, the median, and the mode. But for this analysis today, we're just going to compare the mean versus the median. Okay, so these are measures of center. So I'm going to write measures of center right here next to this heading. Measures of center. Okay, so we're going to look at these graphs as we answer some questions. What do you notice about the mean and the median of if the data has a symmetric shape? So we're looking at this one right here, and it's symmetric, and it looks like the mean and the median pretty well lines up with the center. So they're pretty dang close to the same number. So I'm going to say in this situation, the mean equals the median. Okay, now let's look at skewed left. What do you notice about the mean and median if the data is skewed left? So we're looking at this one right here. So here's our center right here, and we're going to compare the mean and the median, and it looks like the mean is less than. So whatever value the average is, the mean, it'll be less than the median. So let's write that in. So the mean will be smaller or less than the median. Okay. Now let's look at our right skewed. So right here, right skewed, if we look at our mean and our median, in this situation, the mean will actually be bigger. Okay, and we're looking at from the center here, the mean is bigger. So I'm going to say in this situation for right skewed, the mean is bigger than the median. Okay. If when you're doing your practice, they ask you what's the best measure of center, basically it's saying what's the closest value or measure to the center of our data. So if it is symmetric, like this one up here, then it doesn't matter. The mean and the median will be pretty dang close to one another, if not equal. For right skewed, do you see that the median is closer to the center right here? So I would say for right skewed, the median is the best measure of center because it's closer to the center, to that top of that wave. For left skewed, it's also the median. So the median over here is also the best measure of center because it'll be closer to the top of that crest right there. So in summary, I guess we can say that regardless of left or right skewed, the median will tend to be the better measure of center in those situations. Okay. Let's go ahead and do some examples of mean versus median together and also identifying the shape of the distribution. So here's page 2. So we have 3 examples at the top. This top left distribution, it is skewed right. And I know it's skewed right because look at this tail over here of data. So I'm going to say this is skewed right. And in this situation, which is the best measure of center? It's going to be the median. Whenever it's skewed, it's always the median. Okay, now let's look at this one here on the right. This one, it's not perfectly symmetric, but it's pretty close. So in order to be considered symmetric, it doesn't have to be a perfect mirror image on both sides. It just needs to be close. So I'm going to say this one looks symmetric to me. Okay. In this situation, which is the best measure of center? Is it the mean or the median? Honestly, they're going to be close to one another, so I can use either. So I'm going to say either are good. Okay. In this last example, what's the shape? This one is going to be left skewed. You see this tail over here on the left? It trails off. So this is skewed left. And whenever it's skewed, regardless of left or right, the median will always be closer to the center. So we're going to use the median to measure center. All right, we've got one more example to do together. So let's look at our final example. In this final example, we're continuing interpreting. So we're going to look at our data distributions. We're going to notice different interesting pieces of information, and we'll make some comparison statements. So let's first look at what this is describing. This is ages of Oscar-winning actors from 1975 to 2004. The top box plot is the female actors, so I'm just going to write this here right next to the top box plot so I keep it straight. And the bottom box plot B, that's the male actors. So I'm going to just label that on there so I don't get it mixed up. The first question asks, what are the median ages for each gender? Okay, so let's read that off. So the median for girls looks like it's about 35. So for women, it's 35. And then for men, the median, I'd probably say like 42. Okay. What comparisons can be made about the male and female Oscar winners? Now, this is very subjective at this point because there's many sentences you can say, and a lot of them are going to be right. So I'm just going to say the following sentence. I'm going to say that male or men Oscar winners tend to be older. because the median, do you see the median is 42 versus 35? I could also say, reverse that and say, female Oscar winners tend to be younger at 35. So either one will work. So let's do the one about men. So I'm going to say male Oscar winners tend to be older. Okay, and once you have a comparison statement, you're good to go. Just move on to the next one. What's the IQR for each group? Okay, so we need to identify the interquartile range for each group. For the girls, for the women, looks like it's about from Q1 to Q3. Looks like it's like 31 to 41. So I'm going to say female IQR is 41 minus 31, it's 10. So their data is not very spread out. It's about 10 years spread out where 50% of their data is, right, for the IQR. For men, so for male IQR, it's going to be from about maybe like 37 years old to 51. So for them, 51 minus 37 is 14. What conclusions can be drawn from this? So looking at these tell us where 50% of our Oscar winners are, like the ages of 50% of our Oscar winners. So for girls, it's within a 10 year range, and for guys, it's within a 14-year range. So I'm going to say that the male Oscar winners, their ages are more spread out. So I think that's a good way to describe this bigger IQR of 14 years. So male Oscar winner ages are more spread out. Okay, our final question has to do with the outliers. Do you see all the outliers over here? All these like asterisks. These are all outliers, right here, outliers. So basically they're data points sufficiently far away from the rest of the data that they're unusual, okay? So what do they represent? So it's winning actors of Oscars, and so what are these dots telling us? That they are Oscar winners who are older, right? Like there's one that's like 61, and then two that are in their mid-70s, and one that's 80. So those are our outliers. So what do the outliers mean? They're older winners of Oscars. Okay, and like significantly older, like older than 60. That was the notes for 9.1c. I hope that was helpful. I wish you best of luck on your practice. Thank you.